Hello everyone, welcome to the lecture number 43 of this NPTEL lecture series on charging infrastructure, and today we will continue our discussion on dual active bridge converters. In the last class or in the last lecture we have seen it comprises of two active full bridges connected on the either side of the transformer having defined turns ratio. This particular converter is called active because actively we can control the VA1 B1 voltage and VA2 V2 voltage, and depending upon the voltage applied across this inductor, the corresponding impedance offered by this inductor, and accordingly the power flows from A1 B1 terminal to A2 B2 terminal, or from A2 B2 terminal to A1 B1 terminal, depending upon the different magnitude of voltage applied and the phase shifter given between the A1 B1 and A2 B2 voltages. Now using that, there are different kinds of modulations which are possible with this kind of converter. So first modulation is simply a single phase shift modulation, where the phase shift is given between the turning on of 4 S1 S2 S3 S4 switches and S5 S6 S7 S8 switches. That means the turning on off instances of S5 switch is shifted by the phase angle delta from the turning on and off instances of S1. Similarly, S7 turning on and off instances is shifted by delta phase shift with respect to turning on and turning off instances of S3, and simultaneously between S6 and S2 and S8 and S4 there will be a phase shift of the delta in the turning on or off instances. Further, here all the switches are turned on and off for half the switching cycle period, and by controlling this value of this delta, one can control the output and the power delivered from A1 B1 side to A2 B2 side. Similarly, apart from this phase shift, one can also give phase shift among the half bridges in full bridge 1 and the half bridges in the full bridge 2. So that means here when we give theta 1 is the phase shift provided between the turn off instances of the diagonal switches of the full bridge 1, while the theta 2 is the phase shift provided between the turning on and off instances of S5 and S8 switches in the full bridge 2. And then I mean delta and theta 1 or delta and theta 2 or theta 1 and theta 2, one can use this only one can change only two phase angles, and that is when we can get the dual phase shift modulation. In the triple phase shift modulation, we have delta, theta 1, theta 2, all the three phase shifts are varied, and that is when one can achieve the triple phase shift modulation. Similarly, one can also achieve along with this triple phase shift, one can also change the switching frequency, because by changing the switching frequency, the impedance offered by this inductance changes, which can control the amount of current which will be flowing from A1 B1 to A2 B2 terminal, or from A2 B2 to A1 B1 terminal, or vice versa. Finally, one can also do the dual phase shift with variable frequency, which is very rarely used, but one can use that, where along with this two phase shift, one can also introduce the change in the switching frequency as well. And with this kind of different modulation scheme, the power flow can be transferred from A1 B1 to A2 B2, or from A2 B2 to A1 B1 accordingly, by depending upon the kind of phase shift one is giving, either the leading phase shift or lagging phase shift one is giving between these two full bridges. Now we were discussing about the simplest single phase shift modulation, where we have assumed our V in voltage is greater than V naught by N voltage, and V naught by N is the voltage which can be applied from A to B to refer to the primary side, and we have taken that where N is nothing but Ns by Np, and we have seen for this thing our the current waveform of the inductor, the current going through the inductor will having a shape something like this. Now let us try to find out how we can design this L value, and what can be the maximum power which can be transferred between V in and V naught. Let us try to find out that particular relationship. So in this, if we look, let us define this four, this has particularly has four mode 1, mode 2, mode 3, mode 4. And if you look very carefully, if we simply draw this thing in this one, I have IL T, it goes from, if we take, it goes from here, very sharply rises, then slowly rises, then falls down till this one, and then finally at this point it touches, and then again from here the next phase starts. So this is the entire Ts duration we were having. In that Ts duration, this slope is given by V in plus V naught by n. This slope was giving V in minus V naught by n. This slope was giving minus V in minus V naught by n. Okay, obviously everything will be divided by L, and this one will be minus V in plus V naught by L V naught by n divided by L. And if we see in all the three things, let us define some of the things here. Now from here to here it is delta star Ts by 2, and from here to here we have 1 minus delta star Ts by 2. And if we see our this thing, let us define from this point to this point is our T1 point, from this point to this point is our T2 point. And here we have taken I naught, I1, this is I2, this is I3, and this is I4, and we have already defined my I naught is equals to minus I2, which is nothing but equal to I4, and my I3 is equals to minus I1. Now let us try to find out the value of inductance L. Now the value of inductance L, if we try to find out, so let us try to write down first thing, we can just write T1 plus T2 is nothing but equal to delta star Ts by 2, and then we can also write this slope. If we see this slope we have slope of this line can be given as minus I naught by T1, and this is nothing but equal to uh, I1 by T2, and that we can write down I2 by T1 is nothing but equal to I1 by T2. That we can write. Let us define this as equation number 1. Now what we can do is we can now find our this particular slope. If we see, we have L di, which is nothing but going from 0 to I1, L di by dt, which is nothing but T2, is nothing but the slope is V in plus V naught by n. Now this is the thing. Let us define this as equation number 2, where we know that our delta star is nothing but delta by 180 degree, where delta is nothing but the phase shift in degrees. Now then after that, let us go ahead and then define my this particular from here to here. Let us try to define this thing. From here to here it is going from I naught to I1, so I can write expression nothing but I1 minus I naught is nothing but V in plus V naught by n by L delta star Ts by 2. And similarly we can write from this point to this point is nothing but I2 minus I1 is nothing but V in minus V naught by n by L into 1 minus delta star Ts by 2. And we know that as I naught is nothing but equal to minus I2, so we can then write our I1 plus I2 is nothing but equal to V in plus V naught by n by L into delta star Ts by 2. Now this we can define as equation number 3, this we can define as equation number 4. So by solving this equation, that means summation of these two equations, what we will get is our I2 value is nothing but equal to Ts by 4L 2 V naught delta star by n plus V in minus V naught by n, and this let us define this as 5. This is done by solving 3 and 4. Now that means if we have this I2 value, we can then get I1 value to be nothing but equal to Ts by 4L 2 V in star minus V in plus V naught by n. That we can then define it as a equation number 6. So that indicates, if you look here, this since we have defined T1 going from this point to this point, so we can write down this T1 to be equal to nothing but delta star Ts by 2 minus T2, and this T2 we can write down from equation number 2, which will give us nothing but value to be T1 to be delta star Ts by 2 minus L I1 by V in plus V naught by n. This is from equation number 2, and this, when we substitute I1 from 6, what we gonna get is our T1 value to be nothing but equal to Ts by 4 V in plus V naught by n, and this whole thing is nothing but 2 V naught by n delta star plus V in minus V naught by n, and this is nothing but equation number 7. Now similarly we can then define our T2, which we will get by solving this expression, which we will get nothing but Ts by 4 V in plus V naught by n. This will be 2 V in delta star minus V in plus V naught by n. This we will obtain it by using this particular expression. You can obtain that, and this is nothing but equation number 8. Now after knowing this T1 and T2 time instances, this time instances and this time instances, what we have to find out is that, what we will see is that this particular part from this point to this point, if we see, this is nothing but my Ts by 2 period. Now if we see my Ts by 2 period, what we are going to see is that in Ts by 2 period we have the current going from I0 to I1, then I1 to I2, and what we will see is that this variation of this IL current repeats itself after the Ts by 2, that means when it is going from I2 to I3 and then I3 to I4. So we can say that this IL is repeating itself after Ts by 2 period. So if we have to find out the IL average, we can find out by doing the averaging over the Ts by 2 period. Now if we see in our circuit, this circuit, if we see whatever the average value of IL current which we are getting over here will be the same current which we are actually drawing from the input source, and that we can define it as a I in average. So that much current is been drawn from this input, so that the same amount of average current will be drawn from the input, so because this average current will be nothing but the average current of this IL. So what we can then write down is that our I in average is nothing but, we can write down IL average over the Ts by 2 period, as the IL repeat itself after Ts by 2 period, and then if we have to calculate the IL average over this Ts by 2 period, what we can do is we can then do a simple, we can then calculate this area under this curve, that means this particular part, this particular part, and this particular part. We can just take the area of these three portions and we can obtain our required expression, or our required IL average. So what we can do is, it is nothing but, since we have to calculate in Ts by 2 period, so we have taken the mean on that, and let us take in this triangle, which is nothing but half I0 times T1, that is the area of this particular triangle, but and we know that I0 is nothing but equal to minus I2, so we can write down half I2 T1 plus the second area, which is nothing but again a triangle, which is having the uh, height nothing but I1, so we can then write half I1 T2, and then we can just see the third portion, which is nothing but trapezoidal. So we can then write the area of the trapezoid nothing but half I1 plus I2, and the time period, which is nothing but 1 minus delta star Ts by 2, and this is nothing but is our entire area under this curve, which is shown in the shaded red portion. So now let us try to put the T1, T2, I1, I2 values from our previous derived equation. So we can then obtain from 7 we can obtain T1, from 8 we can obtain T2, from equation 5 we can obtain I1, and from equation 6 we can obtain I2. So you can obtain all those uh, scenarios, and then from 5 we can obtain I2, sorry, from 5 we can obtain I2, and from 6 we can obtain our I1. Now this, when we put these particular expressions of T1, T2, I2 and I1 in this particular big expression, what we gonna get is I in average is nothing but equal to 1 minus delta star to delta star V naught by 2 and L FSW, where our FSW we can get it nothing but equal to 1 by Ts, and we can then rewrite this particular expression in one more form, which is 1 minus delta by 180 degree into delta by 180 degree into V naught divided by 2 and L FSW. Here the delta has to be in degrees. So then we can then write our P in average, or the average power which is drawn from the input voltage source. It is nothing but V in times I in average, and that will give me my P in average is nothing but equal to 1 minus delta star times delta star V naught V in by 2 and L FSW. Now from the power balance, what we can write is, from the power balance what we can write down is that my P naught average, that means the power, average power at the output, is nothing but equal to average power at the input, and then we can define that term to be P average, or the average amount of power which is being transferred. So we can write down the average power transfer is nothing but 1 minus delta star into delta star V naught V in by 2 and L FSW. Now this is, let us define this as equation number 9. So we can see that the average power transferred from input side to output side can be obtained by this particular formula. Now let us try to understand, this is the average power which can be obtained at the output. Now let us also see what is the maximum power, average maximum power which can be sent. So for that, what we can do is, we can then divide this P average by, with respect to delta star, and that we can make it equal to 0, and that will give you nothing but 1 minus 2 delta star equal to 0. That implies my delta star is nothing but 1 by 2, and which indicates that my delta value is nothing but equal to 90 degree. So what it indicates, that we will obtain maximum value of P average at the point where our delta star is equal to half, or we can say that our phase shift between the turning on instances of the diagonal switches is nothing but equal to 90 degree. So which indicates, if we put delta star in equation number 9, what we will get is our P average maximum is nothing but V naught V in half times half divided by 2 and L FSW, and that implies my P average maximum is nothing but equal to V naught V in by 8 and L FSW. Now this is the expression which will define how our what is the maximum power we can transfer it from input to output side. Now The same thing we can get when we are doing from power transfer from V naught to V in, the same expression we will get. So, we will now see how our average power varies, with the delta star, and we can then also write parallelly how our power varies with delta, average power varies with delta. So, what we will see is that this expression will become 0 whenever the delta star becomes 1, and this expression will also become 0 whenever delta star is equals to 0. So, we can then define 2 points 1, 0 and 0 and let us say 1, and we know that our maximum value of power reaches at half the point. So, we can then define our value half here, and what we will get is we will get a curve, a parabolic curve which looks like, let me define this at midpoint, which is nothing but goes like this and then comes back and then comes back like this. So, and this point is nothing but your P average maximum value, which is nothing but V naught V in divided by 8 and LFSW. Similarly, in terms of delta, we can say we have 180 degree whenever the delta star is equals to 1, we have 0 degree whenever the delta star is equal to 0, and then we have a 90 degree whenever the delta becomes equal to delta star becomes equal to 1 by 2. So, what we will get is we will again get the same variation, parabolic variation, having a maximum value at delta equal to 90 degree and going there. So, this point is nothing but my P average maximum, which is nothing but V naught V in divided by 8 and L FSW. Now, after obtaining this maximum average power which can be obtained at the output or which can be delivered at the output, what we have to find out is what is the maximum limit of inductance L which we can or what is the range of inductance L which we can put in. So, let us try to see the values of L. That means we can now define some conditions, that means for the minimum value of V in, because generally, and the minimum value of V naught, that generally because you have variation in the input and output voltages, you have some ripples which, so that means the V in and V naught goes somewhere between minimum value and the maximum value. So, let us define that minimum value of V in and V naught, so we can then able to transfer with the minimum value of input and output voltages, transfer maximum power. So, we can able to transfer P average maximum with minimum value of V in and V naught only when our L value is less than equal to V in min, V naught min divided by 8 and FSW and P average maximum. Now, if you see this particular part is generally given in the specification. This and this is also given in the specification of the converter whenever we are starting designing the converter. F switching is the designer's choice depending upon the switching laws in the converter. One can decide what could be the maximum switching frequency, and depending upon the size of the transformer, one can decide what could be the switching frequency limit we can go. So, that is the designer's choice. Similarly, number of turns is also a designer's choice, depending upon the various circuit parameters like different RMS currents at the transformer, at the switches on both sides of the full bridges. Designer can choose what will be the best possible number of turns one can have, and that will give you nothing but maximum value of L. So, this is the maximum value of L you will get. Now, the designer can do the iterations and can able to predict what could be the best possible value of inductor such that you will have the minimal losses as well as the maximum power density. That means you can then define your number of turns, your switching frequencies, and then can optimally select the this inductance value. Similarly, we can also define the constraints on the delta star, because you know the delta star corresponds to the phase angle, what can be the maximum phase angle. So this delta star, because it is a generally these control schemes are developed in the microcontroller, so this delta star cannot go maximum or cannot go beyond a certain minimum value. So generally it is been clamped up to 0.5, and maximum side it goes up to 0.95. So this particular range can also be taken, and depending upon the required amount of power to be transferred from input to output side, and with this range of delta one can also decide what could be the minimum value of L one need to have to allow the required amount of power transfer to be done from input to output side. So this is how one can select the inductance which is being used to actually facilitate the required amount of power transfer from input to output side, or from one side to the another side. However, as we have discussed in our this DAB, we have several other modulations which are possible, like dual phase shift, or we have our triple phase shift with variable frequency. So for different modulation schemes, one can then define these different inductances value which can be used. One can either reach to the closed form solution, or one can do the optimization such that we can achieve the inductance value to be smaller. At the same time, the RMS ratings of the switches as well as the inductor are also smaller. So one can do that optimization and can arrive at what will be my number of turns, what will be my inductance. So here if you look very carefully, this waveform is there whenever we have V greater than V naught by N. Now let us also see how the inductor current varies when we have V less than V naught by N. So let us see how the waveforms look like. Now let us take our the condition when our V is less than V naught by N. So if you look very carefully, I am now drawing only VA1 B1 because we already know how VA1 B1 can be obtained. So if this is for TS by 2, if it is like this, for another TS by 2 if it is like this. Similarly for VA2 B2, assume at this point my this A2 B2 is going like this, and then again it goes like this here. So this is minus V naught by N, V naught by N, and then again minus V naught by N. Here this is referred to primary side. So if we see our inductor waveform, IL, this is my V in voltage. So at this point my thing will be going again sharply like this, with a slope V in plus V naught by L, or V naught by N by L. With that slope it is going. Here if we look, it is V in minus V naught by N, and since it is V in is less than V naught by L, so we have a negative slope which goes like this. So it will become V in minus V naught by N divided by L. With that slope it is falling. Since my V in is less than V naught by N, so I have a falling slope here. And this continues not up till here, this continues up to this point, and beyond that point my this voltage is minus V in coming over here, minus V in, and I have minus V naught by L. So it is again falling to this one sharply, which is falling down. So this will be, or you can say this further sharply going down. Okay, this slope is nothing but minus V in minus V naught by N by L slope we are having. And finally from this point to this point, what we have is, we have the slope which is going in this way, and this slope is nothing but my minus V in plus V naught by N by L. Since my V naught by N is greater than V in, so this slope is positive slope. And if we look very carefully, this one and this one is I naught, again here we can say I4, this is I3, this is I1, and this is my I2, and we can say that my I2 is nothing but minus I naught is nothing but I4, and here we can say that my I1 is nothing but equal to minus I3. We can also draw much more simplest manner in this. We have this one, we have sharp slope like this, goes layer, and this one is minus Vn plus V naught by N by L. This slope and this slope is the nearly the same. When it is falling, it is rising. So we can then see our the current waveform, current shape. If we see V in greater than V naught by N, we have shape going rising up, then again rising, then falling, then falling. However, in this case, our shape of the waveform will be rising, then falling, then falling, and then rising. So our shape of the waveform changes, and then one can easily find the RMS current of this particular waveform and can able to understand what could be the impact of V in greater than V naught by N or V in less than V naught by N, and then can able to understand for the smallest value of RMS current of the inductor one can choose the number of turns, n number of turns, because here my V in and V naught is fixed. If I change the n value, I can make either V in greater than V naught by N or V in smaller than V naught by N. So that iteration the designer has to do. Here if you look very carefully, is nothing but delta star Ts by 2 period. Here we are giving the switch S1 and S4 is on, here my S2 and S3 is on. Here if we look very carefully, here my S5, if you see, S5 and S8 is on, and here my S7 and S6 is on, and here my S7 and S6 is on. So the phase shift between S1 and S5 is given by delta Ts by 2, and S4 and S8 is given by delta Ts by 2. Similarly, the phase shift between S2 and S6 and S3 and S7 is giving the phase shift of delta Ts by 2 accordingly. Similarly, one can also see how we can obtain the for backward power flow. Backward power flow, how we can obtain? There we have provided the, if you look very carefully, here also we have provided the lagging phase shift of VA2 B2 with respect to A1 B1. That is when the power is transferred from A1 B1 terminal to A2 B2 terminal. However, if we wanted to reverse this thing, we have to provide leading phase shift in the A2 B2 as compared to A1 B1. So that we can just quickly let us draw and see how the waveform look like. VA1 B1, and this is VA2 B2 referred to primary, and we can then also see how my IL changes that. So here we assume the same thing, we have Ts by 2 period it is on, and Ts by 2 period it is off. So this is my S1 S4, and sorry, this is off means we are applying minus V in, here it is V in. So here my S2 and S3 is on. Now if we look A2 B2, since we have given the leading phase shift, so at this point my phase shift changes from this value to this value, then goes from this value to this value. So here I am now applying V naught by N, and here minus V naught by N, and here my S5 and S8 is on, and here my S6 and S7 is on. And if you look very carefully, similarly in this also we can define our this period is nothing but 1 minus delta star Ts by 2, and this period is nothing but delta star Ts by 2. So this is what we have given, and let us see our waveform, how our waveform changes in this particular thing. In this particular thing, since my voltage at this place is having something like this waveform, which is again here we have considered my V in is greater than V naught by n. So here the slope is V in minus V naught by n by L, positive slope we are getting. Here if we look very carefully, it is V in minus of minus V naught by n, so we have positive slope, which is V in plus V naught by n by L we got here. Here minus V in is applied and minus of minus V naught by n, so it is again we have a negative slope which we have here like this. So we will have something like this waveform where it is nothing but minus V in plus V naught by n, this divided by L, and finally at this place we have minus V in and plus V naught by minus of minus V naught by n, so we have this going like this. This is I naught, this is same as this one I4, and this is I1, this is I2, this is I3. Here also we have the same thing, I naught is equals to I4 is equals to minus I1 and I2, so minus I2, and it is I1 is equals to minus I3. And if we look during this point, we have minus V in minus V naught by n by L slope we are having. So here when we do the averaging, we can get the P in average to be nothing but minus V naught V in delta star 1 minus delta star divided by 2 n L FSW. That one can get from by just following the same step what we have done for the forward power flow. Sorry, here it is plus sign. Here we have given the phase shift in the A2 B2 in the leading direction, because power always flow from leading phase shift to the lagging phase shift. So accordingly one can calculate the backward power flow. Similarly, one can also see how my inductor current changes with triple phase shift as well, where when we have the triple phase shift we will be introducing zero state in the A1 B1 and A2 B2. So similarly one can also do it for triple phase shift modulation, and again we are now here drawing V in greater than V naught by n. So let us see how our waveforms look like. If you look very carefully, first let us draw VA1 B1, and then let us draw VA2 B2 referred to primary side, and then finally let us draw my IL. So if we look very carefully, since we are having triple phase shift, that means we are having delta, theta 1, theta 2. Theta 1 indicates there is a phase shift between the turning off period of the diagonal switches. That's when we are now seeing the zero state applied from the A1 B1 side, and similarly the zero state from the A2 B2 side. So let us see how our zero state look like. So let us first draw our circuit. First it goes here for some time, it goes to 0, then it goes 0 for some time, and after that we have minus here V in voltage applied, minus V in voltage, here 0 voltage. So till this point it is Ts by 2, and then again it is 0 applied, and then finally it goes till this, finally it goes up to this point, and this point if we say this is Ts by 2, this is again Ts by 2. So for some period we are now applying 0 voltage from the A1 B1. In A2 B2, along with the 0 voltage we are also applying some phase shift. So let us define this phase shift to be delta, and this was previously it was 0, it is 0, then it is delta, is 0 applied, then it zeros continues, and then again it applies as V naught, then goes like this. So here it is V naught by n minus V naught by n. This value is nothing but delta star Ts by 2, and then from here to here it is 1 minus delta Ts by 2. So then if we look very carefully, we have several other, you know, time period we have got something like this. There will be several steps in the IL waveform. Now if you look very carefully, during this time it is 0. So here if we see it is V in voltage apply, let us say it starts from 0. So it goes here. So we will have V in by L with slope, with that it is rising. Then at this point it is V in minus V naught by n by L, slope it is rising. Here it is minus V naught by n, it is falling. So assume we have reached to, you know, assume we have reached to this point. So it is, you know, minus V naught by n by L, slope it is falling. From here to here it is 0, exactly 0 it is having, and then from here to here it is minus V in voltage is applied. So it again goes down. So it again goes down. So let us take it goes down like this. It is nothing but minus V in by L voltage, it is falling down. Here it is with 0 slope, it is there. From here to here it is minus V in plus V naught by n. So it is falling, but it is falling with this one minus V in plus V naught by n L, it is there. And from here to here it is having some positive slope. Assume it goes something like this. This is V naught by n L, it is rising, and then from here to here it is 0 slope. So with this kind of thing, you see there are several segregations or several parts of this inductor current, and then one can find out the RMS current of this, and then able to understand which modulation schemes will give the reduced RMS current of the inductor current, because the RMS current of inductor current is actually tells you the RMS current of transformer windings, because the same current is going through the transformer windings, and it will actually determine the currents of switches as well, because the same amount of current will be drawing from the switches. So it is important to see, for the same amount of power transfer from A1 B1 terminal to A2 B2 terminal or A2 B2 terminal to A1 B1 terminal, one can do either SPS modulation or DPS modulation or TPS modulation or TPS modulation with variable frequency or DPS with variable frequency. Any kind of modulation one can do. So anyone can apply different modulation scheme and can then calculate the RMS currents which is flowing through the inductor, and then select that modulation scheme which has the minimum RMS current, and that is when one can ensure that they have the minimum conduction losses in their converters, because this RMS current of the inductor will indirectly determine the RMS current of the transformer windings as well as the RMS current of the switches, because in this period some switches are on, in this period some other switches are on, in this period some other switches are on. So one can then find, once they have the RMS rating of this IL, one can then calculate, depending upon for how much time it is being conducted, one can calculate the conduction loss of those switches as well, which we have discussed in AC/DC converter. The same concepts can be applied over here as well. Now if you look very carefully, this is the DAB converter. Similarly, there are other derivatives of DAB converter one can have. One can have, you know, resonant DAB converters, where instead of just using the square voltages at the terminals of transformer or terminals of series connection of inductor and transformer. One can apply the sinusoidal voltages by just giving the resonant network, uh, by putting the resonant impedance, something like this. One can apply V in, V naught. One can put C and L, and then you can do the resonance between C and L, and that's when, instead of directly applying the square pulses at this A1 B1 terminal, because of the resonance, one can nullify the other harmonics and can then allow only the switching frequency harmonics to be applied from the transformer primary winding. That means one can now apply the sinusoidal voltage from A1 B1. Similarly, one can also apply the capacitors on the other side as well, and can also do the resonance between this thing, and that's when we can get. Similarly, one can also get the multi-level DABs. Multi-level DABs, one can, instead of putting this half bridge comprises of two switches which can apply only two level of voltages, which is with respect to n, one can apply only V in from this point A1, between A1 and N, V in or 0. Instead of that, one can also use multi-level half bridges, like 3-level half bridges or 5-level half bridges, in all the 4 half bridges or in one of the half bridges. Various combinations are possible, and one can then make sure the RMS current flowing through the primary side and secondary side are minimal, and that's when one can reduce the overall conduction losses in the converter. Similarly, there are also multi-level DBs are, then they are also modular multi-level DBs are also there. However, this we are not covering in this lecture, but this can be looked upon for further higher power rating design of the power converters. One can look for this kind of derivative of this DB converters, one can look at. So these are some of the isolated DCC converter we have discussed. In the entire this power conversion unit, we have discussed in detail about AC-DC converters, different kinds of AC-DC converters, single phase, three phase. Then we have revisited some of the isolated DC-DC converters, and then in isolated DC-DC converter we have discussed in detail phase shifted full bridge converter and the our dual active bridge converter. And there are also another topologies which are there, which is the resonant based converters called as the LLC converters are also there as one of the converters which are used very frequently in the applications where you wanted to have a step down operation. So one can look for LLC based resonant converter as well, which has the transformer isolation. However, we will keep our discussion up till DAB converters only, and because lot of literatures are available where they discuss in detail about LLC resonant design of LLC resonant converters and all. So these are the different isolated DCC converters which are being used in the power conversion unit of your EV chargers. Most commonly used are PSFB and DAB, which we have discussed in detail. And also for step down operation, one also sometimes used LLC resonant converter as well. So we will restrict our discussions up to these topics, and we will discuss from next class onwards the concepts related to, in most of the isolated DC converter we have this transformer. So we will see in brief how one can design the transformer, isolated transformer for this kind of converters, and then we will proceed further discussing on the different communication aspect of the EV charging system. Thank you very much for patiently listening to this lecture, and we will see you in the next lecture.